Okay, our next talk is technology advancements enable next generation SATCOM and space-based radar, presented by Mike Jones, System Platform Manager, and Brad Hall, Systems Application Manager, Aerospace and Defense at Analog Devices.
Hi, thanks for having us today. Today we will be presenting on technology advancements that are enabling some of the latest architectures for SATCOM and space-based radar. I have with myself Mike Jones, and he'll be covering the second half of this presentation. So what will we be covering in today's presentation? We're going to start with a high-level overview of some of the challenges that we are seeing in our customer interactions. We're going to go through a few very high-level trade-offs for analog, hybrid, and digital beamforming, which is a major driver for some of the architecture decisions that our customers are facing. And then we'll do a little bit of a signal chain overview, going through the beamformers, the signal chain frequency converters, the digitization and DSP, and just hitting on a few of the key challenges that we see from our customers and the corresponding underlying technology that is helping to solve those challenges. We'll also go a little bit deeper into efficient partitioning of DSP resources in these signal chains, and that's where I'll hand it over to Mike, and then we'll conclude. So getting into some of the trends and the corresponding technologies, one major trend that we see is multifunction and reconfigurability. Having the ability to repurpose constellations and satellites and how they're used over time, and adjusting as things change on the ground. How is this rolling into technology? It's requiring software-definable payloads, able to change their frequency bands, their instantaneous bandwidth, the performance versus power trade-offs, the number of channels, beams, things like that. Wider frequency coverage, so being able to cover from L band to up to Q and V band, which are emerging SATCOM bands. And then the hybrid and digital beamforming architecture is enabling some of these other things, you know, having more beams, trading off power and beams. So these things all roll into multifunction and reconfigurability. There's also many more satellites. This is leading to more congestion in the constellation. The satellite payload needs to be able to handle interferers, leading to signal chains with higher dynamic range, as well as spatial filtering. Evolving reliability standards, so the trade-off between cost and screening of the components that are underlying. How much testing do you need to do? And that's especially relevant to some of the new LEO constellations that are coming out. And then higher demands on SWaP-C, so that's size, weight, and power and cost. So many more satellites that are smaller in size, trying to condense the amount of functionality into a smaller area. This is leading to new techniques for integration, monolithic and heterogeneous integration. And then taking a close eye at how we are partitioning the system elements. So that's another key technology that's being focused on here. So this is a big topic, you know, the architecture decisions that go into digital, hybrid, or analog beamforming and where exactly they fit in the constellation. This is intended to give a brief overview of some of the high-level trade-offs. As you can see here, what we have shown on the slide is kind of the progression from analog beamforming on the left to digital on the right. Analog beamforming, which is performing the phase and amplitude adjustment in the RF domain. And typically this is a low power solution. It's a single beam, can be implemented as a planar array. Multi-beam analog then builds on that and provides a bit more complexity for the array and allows more analog beams to be integrated, so it has a larger size, it's more complex. Hybrid beamforming takes that and splits it up so that you have multiple subarrays, and then the beamforming happens in the RF domain. So there are phase and amplitude shifters in the RF domain as well as the digital domain. This is a little bit higher power because you need more digitizers, but you can accommodate many more beams in this case. There is a downside, there are some downsides here, the poor side-low performance, but that can be mitigated through various techniques. And then lastly is digital beamforming, which is essentially a digitizer behind every element. This is an emerging field in SATCOM, able to handle many beams again, and has high level of reconfigurability, but it's also the highest power. So there are some challenges there. From our viewpoint, hybrid beamforming is the near-term focus, and it covers many use cases, and in general, many different systems are using hybrid beamforming now. So what we want to do next is go through and step through this signal chain, not in too much detail, but kind of walk through each subsection of the hybrid beamforming signal chain. We're going to start with the element subcircuits, which include the BFIC, the splitter network that I talked about, the LNAs and PAs, and then move on to frequency conversion and clocking. From there, we'll get to digitization, and then processing and calibration. And throughout, we're going to keep an eye on the efficient use of resources to accomplish the system goals. So getting into the element subcircuits, the table that we have presented here is a list of the key challenges on the left, mapping to some of the technology advancements that are needed to address those key challenges. So we have low G over T, which sets the main performance of the receive array for a phased array. We have low power. Of course, every element every circuit in this section of the signal chain scales. So every element has an LNA or a PA, a BFIC that corresponds to it. So low power is critical at this node. Half element lambda over 2 element spacing. So this places a size constraint on the elements in this circuit. That's where some of the integrated semiconductor products like SIPs and other packaging techniques come into play. And then wide bandwidth. So one thing that we're seeing is a much wider instantaneous bandwidth, higher frequency coverage for these applications, and that leads to what is called beam squint, which is essentially a change in steering angle as the frequency operation of the array changes. This is dealt with a true time delay rather than a phase shift element in this circuit. And then lastly, beam management, with the potentially hundreds of beams or thousands of beams, it does become a logistical challenge to actually manage the coordination of the analog front end and the digital back end. Moving on to frequency conversion. Some of the key challenges here are frequency planning, reconfigurability of this signal chain, ensuring that it's a wideband tunable down converter or up converter. Managing the size and the power. This is one area where heterogeneous integration or monolithic pulling the functions into a SIP or a RFIC helps with getting the size down and maintaining the overall form factor that's required. And then LO clock generation, distribution, and synchronization is another key when you have multiple channels that all need to be phase synchronized with each other. It's critical to maintain synchronization across this, as well as across temperature. And then the last one here, before I pass it off to Mike, is digitization. And some of the key challenges here, synchronization again, you need to synchronize the RF domain. You also need to synchronize all of the digitizers in your array. Wide instantaneous bandwidth, which this kind of gets back to the congested spectrum that I mentioned at the beginning, where with more satellites, you're going to have more interferers, intentional jamming in some cases, and that in tandem with a wide instantaneous bandwidth opens up your receiver for potential issues. So high sample rates for high instantaneous bandwidth are required, and high dynamic range of the data converters is required in order to manage the potential interferers in your signal chain. The image in that, in this case, is showing an interfere, a desired signal, and a spur that results from the interaction of the interfere and the signal. And so maintaining a high dynamic range is critical there. And then lastly, reducing the power consumption. And this is where Mike will get into some details here on the hardened DSP features.
Thanks, Brad. So what we'll talk about here is, so there's the conditioning of the signal chain, and then there's the mixed signal aspects of a radar and a phased array system. And in particular, what we're liking to show here is the ability of using hardened DSP now in our digitizer ICs to allow us to calibrate these multiple channels in your phased array radar and how it relates to satellite communications. Historically, digital signal processing blocks have resided largely within soft fabric of an FPGA. And physically, these would reside in different DSP blocks throughout the FPGA. And one would be required to synthesize the design, make sure that it meets timing and those types of things. And due to the physical locations of these things, it could burn substantial amount of power to implement these types of calibrations needed for multi-channel systems. And so now what we see as a trend is a migration toward hardened DSP, physically residing on digitizer ICs, right on the digital domain of the ADCs and the DACs. And so what we have looked at is how can these hardened DSP blocks be leveraged for satellite communications, for multi-channel system radar systems. One thing that is required for any multi-channel system is you want to have a deterministic phase. You want to have a deterministic phase in terms of a known relationship with your phase for multiple channels. You also want to have the ability to do multiple channel amplitude corrections and have flat responses across frequency in your full IQ bandwidth. And so what we wanted to do was to actually build something that allowed us to leverage this hardened DSP and see how it applied to SATCOM. The physical blocks that we'll be talking about in terms of DSP are taking the shape in the form of programmable finite impulse response filters, digital filters, as well as digital down converter and digital up converter, DDC, DUC blocks that are in the digital domain behind the ADCs or in front of the DACs. And so within, if you look at the bottom left here, with this particular, oh my goodness. With this particular with this block diagram, what you have is 3 sub-blocks within a DDC. So you have the first block that is frequency translation stage. And so within that frequency translation stage, you have a numerically controlled oscillator. And for those in the RF and microwave domain, that's essentially the equivalent of a LO, a local oscillator. At the output of those NCOs, you have phase adjustments on a per channel basis to allow you to tune the phase of each of the individual channels. And so we leverage this in our multi-channel systems. And then down the road, you have a decimation sub-block within the DDC. And what this allows you to do is to have the ADC sample at a different data rate, or a sample rate than the data rate coming off of the final digital interface to the chip. And then you have digital gain, which allows you to ensure that the gain ranging of your system is sufficient for your application. And so we're leveraging these DSP blocks in terms of SATCOM to allow us to calibrate the full system. This just shows a hardware platform which we built to fully demonstrate this DSP capability. So what you see is on the top right is a 16-channel transmit, 16-channel receive phased array SATCOM development platform, leveraging backbone ICs that have digitizer ICs which have hardened DSP on them. And in using that, what we're able to do is showcase how we can capture multi-channel responses at the same time and look at how they respond to this hardened DSP being adjusted. And so on the bottom left, what you notice is a 16-channel simultaneous capture receive and introduced phase anomalies into the system. And so with this capture, you notice that there's no phase alignment that's happening in the system. After we measure those phase errors and apply the hardened DSP phase offsets, what we are able to do is align all 16 channels in phase. And so again, this is on the digitizer ICs themselves. And so what you might notice and state is, okay, we can align the phase, but what about the amplitude? And so for amplitude corrections, what we're able to do is leverage the finite impulse response filters that are, again, hardened on these digitizer ICs. And you can do that on a per channel basis. And so this takes advantage of the fact that each channel can have a 96 tap dual reel and hardened DSP to save on power, which we'll show here in a bit. And this just shows how every single FIR filter we were able to apply a channel correction in order to not only help with the phase alignment, but also to correct any amplitude anomalies in the system. And a key point with this was that we're able to use knobs in the digital domain in order to correct both digital and RF and microwave anomalies, which are in the system. This shows a technique we use to allow us to demonstrate the full capability of this. So what you see on the top is a linear frequency modulated signal. All 16 captures in the same instance in time. We set the LFM signal, the linear frequency modulated signal, to be equal to the data rate of the system, so that we could get a measured phase and amplitude response across the full frequency range. And what you notice with that is a few things. The first thing is there's no phase alignment. Prior to the calibration, all the channels are out of phase across all frequencies. But also you notice that the amplitude flatness isn't necessarily good. And so there's also, if we were to zoom in and look at each individual channel, the equalization from channel to channel wouldn't necessarily be correct. So what we did was we leveraged the hardened DSP to allow us to change the phase offsets on the NCOs in the digitizer, and then apply these FIR filter coefficients on a per channel basis and recaptured that same LFM signal. And that's what you see on the bottom, where you're able to correct the phase. You also see a flatter amplitude response, and you see equalization if you were to zoom in on each channel. And so this is what we're leveraging to demonstrate how we're able to achieve benefits in phased array radars and in satellite communication systems. And our customers have adopted this for many of their instances. And so it's great. So we can align, we can calibrate these systems, these multi-channel systems using hardened DSP. Then what do you do with that? And so for us, what we wanted to do was simulate a radar-like situation where we send out 8 transmit channels that have been phase aligned and corrected. And then we have a loopback signal back into all 8 receivers. And so you notice just with the sinusoid here that you're able to align all the channels. And so the phase and the amplitudes look in line for all 8 channels. If you do an FFT of each of those, you notice the individual responses in the middle for all of those. And so what you can get is, for a single channel, if the single channel doesn't meet your radar requirements, what you can do is you can coherently combine these channels and allow you to achieve greater dynamic range. And so if you notice the noise floor with the individual channel in the middle, hovering somewhere, call it around 85, 90 dB of dBFS. After you phase align and combine those channels, you see on the bottom, the noise floor hovers closer to 95 dB. So you get this 10 log n improvement for every n channels in your system. Also of note is you can force spurious to be decorrelated. And so what you see here at around -7 megahertz in this, how the amplitudes in the middle are larger than after you phase align and combine in the digital domain. And again, this is leveraging Hardened DSP. To showcase a little bit on the transmit side, so the previous was on the receive side and the transmit. This shows how when you combine in the transmit side phase aligned signals and then recapture that, you can actually have improved dynamic range. And so this is data taken off of that system that you saw earlier. And really for us, we were somewhat limited just to the spectrum analyzer we were using to compute our SFDR numbers. And so there's times where we saw 90 dB SFDR on the transmit side for 16 channel combined system. So we were very excited about this. And again, this is leveraging the Hardened DSP for SATCOM. One of the key points was so you can achieve these system level benefits, and one of those large benefits is power. So if you think about how the logic is residing in a soft fabric, what you would have is to measure, so synthesize a FIR filter in the FPGA, measure its power consumption, then do the same hardened FIR filter power consumption in a digitizer IC. And the results were pretty astounding in that you get half as much power consumption by leveraging this Hardened DSP capability. And then additional to that, what you see is the available resources. So if you look at one of the largest soft fabrics out there, what you can do is you notice quickly that to get wideband FIR filters, for instance, on a per channel to do these calibrations for SATCOM, you require on the order of 3.5 times the available resources on these type of devices. And so that's something that's realizable at the digitizer IC itself on a per channel basis. We've done a lot of other work to discuss these system level benefits of Hardened DSP or digitizer ICs. And so these are just a few examples of that work that we have going on. But at that, I'll just hand it back to Brad for a wrap up, and thanks for your time.
Great, thanks, Mike. Okay, so just to pull it back into what we talked about and conclude the presentation here. There are key trends driving some of these technology needs. So we talked about some of the trends at the element sub-circuit level. It's all about scalable architectures, low power, and true time delay beamforming components. For frequency conversion, it's about decreasing the size, low swap, size, weight, and power, heterogeneous integration, and wideband systems. And then, as Mike showed with the digitization and the Hardened DSP, it's about increasing the sample rates to achieve, to achieve wider bandwidth, but also along with high dynamic range, and we showed some of that. And then the efficient use of DSP resources, pushing those resources closer to the antenna is going to save power in the end for the system. So with that, I thank everyone for listening, your attention.
Any questions?
So you showed that evaluation board where you were doing the time alignment and the amplitude alignment. Was that done at the plane of the ADC front end? And could it be extended to the actual array to compensate for the array? I presume you have some kind of reference signal that you feed to all of them to do time alignment and so on. I'm interested in how that would scale to something that would be in space at the actual array itself.
That's right, yeah. So for that calibration, it corrected the digitizer itself, but also the RF and microwave front ends. I didn't show it, but we also have a planar array that attaches to it to demonstrate over-the-air beamforming. And so we're able to calibrate at the element level itself for this. That was for over-the-air calibration, that's correct.
Anyone else?
Thank you both. The ADC has moved, as you say, it used to be original just an ADC, and all the DSP was in the FPGA, and then a lot of the DSPs moved forward. And in the first part of the talk, you talked about system in package, which was more RF, I think. I mean, are you looking in the future to maybe do a system in package where you combine some of the ADC, DSP, and some of the RF elements, or is that maybe a step too far?
Yeah, that's certainly been considered. I think in general, what you see is, with our ADC roadmap is integration at both ends. I mean, there's the clear integration of DSP into the ADC, but there's also advancements in the ADC technology that mitigate some of the needs of the RF front end. So it's kind of it's not necessarily like we're pulling in RF components, but the ADC architecture is influencing the RF architecture in a way and really minimizing some of the needs in the RF front end. For example, for like direct sampling, as the ADCs are able to, take in higher frequencies, it's going to remove mixing stages and other things like that in the RF front end.
Any other questions? Thank you.